Okay, so a quick review of the textbook, and then I'll go to our more structured notes. So, force is a vector, and Newton's first law states that the force acting on a body, the net force, is zero when the body's in equilibrium. If the body is initially at rest, it remains at rest. If it is initially in motion, continues to move with constant velocity. Now, Newton's second law is basically this formula. The net force equals mass times acceleration, which you can get to be acceleration equals net force over mass, and mass is in kilograms. We also know about this equation. Weight equals mass times the acceleration due to gravity, and weight is the same thing as the gravitational force. And the acceleration due to gravity, g, equals 9.8 meters per second squared on Earth, and it's positive. Now on to Newton's third law, the force, and notice there's an arrow, so because it is a vector, which means direction and magnitude matters. And so force of A on B equals the opposite of force of B on A. So they are the same magnitude, just different signs, different directions. All right, so now let's get some more structured. That's kind of a preview. I will go a little more in depth now. So, mass is the amount of matter in an object. It does not change no matter what planet you go. So, mass, amount of matter in an object. Does not change when you go to another planet, which is different to weight, which I'll talk a little more about soon. Amount of matter. So mass never changes. So and the units are kg. No matter where you are in the universe, your mass will remain the same unless someone chops off a body part. Okay, now let's talk about inertia. So inertia is not a force. That's a common mistake. Inertia is a property. It's not a force. So inertia is resistance to change based solely on mass. So resistance to change based solely on mass. Okay. Mass. No symbol or units, never used in calculations. Students incorrectly think that inertia is a force. It is not a force. Not a force. More mass equals more inertia. So I have more inertia than this piece of paper because I have more matter in my body. Okay. So a ceramic gnome in your body has more inertia than a speeding bullet because it has more mass. Okay. Force. So basic definition of a force is a push or pull. Push or pull interaction between two objects. So it's two objects. Interaction between two objects. Interaction between two objects due to specific property of the objects. Symbol is a big F. So Fg is force of gravity. I'm going to make these actually dots. So Fg equals force of gravity, which is the same thing as weight. There's Fn equals normal force. Units is N, or newtons. Weight, weight is the same thing as force of gravity. So weight is the same thing as the force of gravity. Commonly, one of the masses is the Earth or some other planet. Symbol in, units, N, or newtons. To find the weight of an object, use weight equals mass times acceleration due to gravity. So weight equals mass in kilograms, acceleration of gravity, or acceleration due to gravity, so on Earth, G equals 10 meters per second squared, or if you want to be more exact, 9.8 meters per second squared. So this is the basics, and then we'll move on to Newton's first law. Let me see if there's anything I can add to this. Okay, so remember, mass is the amount of matter. So I'm going to highlight this in an object. Does not change when you go to another planet. Units is kilograms. Inertia is the resistance to change based solely on mass. Not a force. More mass equals more inertia. Force is a push or a pull. Push or a pull interaction between two objects. Let me add that vector. Force of gravity. Fg means force of gravity. Fn equals normal force. The normal force is the force perpendicular to the surface the object lies on. So this would be normal force because it's perpendicular to the surface it's lying, resting on. Weight, and the unit is Newton. Weight is the same thing as the force of gravity. So units, Newton. Weight equals mass times the acceleration due to gravity on the planet. And so weight depends on mass, as you can see in this equation. So now let's move on to Newton's first law. Newton's first law about inertia. An object maintains its constant velocity unless an unbalanced force acts on it. An unbalanced force means net force. Add up all the forces and you don't get zero. If the net force is zero, then it's moving at constant velocity. So, I'll write the definition here. An object maintains its constant velocity unless an unbalanced force acts on it. Newton's first law. An object maintains its constant velocity unless an unbalanced force acts on it. So, let me out. Where is it? Sorry. Okay. Yeah. So an object at rest will remain at rest unless acted on by an unbalanced force. An object in motion will continue with constant speed and direction unless acted on by an unbalanced force. So say I push this book across the table. Pretend this is the table. It'll stop eventually because there's friction acting, and we will act. We'll talk more about friction soon. So an object at rest. An object at rest will remain at rest unless. So an object at rest will remain at rest. Oops, not unless. And then, unless acted on by an unbalanced force. An object at rest will remain at rest unless acted on by an unbalanced force. So, right, if again, this book is lying on the table, it will only move if an unbalanced force, right, is moving the book. Now, an object in motion will An object in motion will continue this constant speed unless acted on by an unbalanced force. So an object in motion will continue with constant speed and direction. Well, oh, wait, hold on. I wrote this one. An object in motion will continue with constant speed and direction unless acted on by an unbalanced force. Will continue with constant speed and direction with so if there's an initial push, then this will continue moving unless an unbalanced force is acted on it, such as, often the case, gravity. I mean, not gravity, sorry, friction. Unbalanced force equals net force. Unbalanced force equals net force. So net force equals 0, or how I'll put it this way. When constant velocity net force equals 0, or Fn, and acceleration equals 0. Let's do F9. And then acceleration also equals 0. So net force changes velocity and causes acceleration. Changes velocity and causes acceleration. So Newton's first law, an object maintains its constant velocity unless an unbalanced force acts on it. A different way to state this is if there's a net force, the object must be accelerating. If there's a net force, if there is a net force, the object must be accelerating. That's an S. If there's a net force, The object must be accelerating. So in those type of logic problems, if they ask, if they have something that's accelerating, then there must be a net force acting on the object. So, quick review of Newton's first law. An object maintains its constant velocity unless an unbalanced force acts on it. An object at rest will remain at rest unless acted on by an unbalanced force. An object in motion will continue with constant speed and direction unless acted on by an unbalanced force. Unbalanced force equals net force. Unbalanced force equals net force. When constant velocity, the net force is equal to 0 and the acceleration equals 0. So net force and acceleration are very related to each other. So again, when it's constant velocity, when you're moving at the same velocity, there's no acceleration and there's also no net force. Net force changes velocity and causes acceleration. If there's a net force, the object must be accelerating. Okay, so that is the first law. First law. So again, if something's at rest, then it will remain at rest unless there's a force acting on it, an unbalanced force acting on it. If something's in motion, then it will continue to be in motion unless an unbalanced force is acting on it. Okay, Newton's second law, more straightforward. To find the acceleration of an object, first add up all forces acting on it and divide by the mass. So it's A equals F net over M, or F net equals mass times acceleration. The second law. And again, you can rearrange it to get, so acceleration equals net force over mass in kilograms. That's pretty much Newton's second law. Yeah, that is all I have to say on Newton's second law. Acceleration equals force net. And so far we have two equations, right? This one, A equals F net over M. If you have that memorized, you don't need to have this one memorized because you can just derive it. So we know this one. We also earlier learned about weight equals mass times the acceleration due to gravity. These are some equations to remember. Newton's third law. If A applies a force to B, then B applies an equal and opposite force to A at the exact same time. The phrase you can't touch without being touched. Or actually, a little more about Newton's second law. The acceleration of an object depends on the mass of the object and the amount of force applied. Right, so we have the formula net force over mass. So acceleration depends. So if the net force is really big, then the acceleration will be big, which makes sense. If you're pushed very quickly, or there's a big net, or if you're pulling something, you pull a lot, then the acceleration will be bigger. And if the net force is the same but mass is big, then the acceleration will be small. That makes sense. If you're pulling something very heavy versus pulling something very light, then the acceleration will be different. Okay, back to Newton's third law. So if object A applies a force on B, then B applies an equal amount of force then B applies an equal amount of force, an equal and opposite force. Okay, let me just rewrite this. So if object A applies a force to B, then B applies an equal and opposite force to A at the same exact time. Or at the exact same time. So basically it's saying, so the moment has to be the exact same time. So if it's like 2 seconds later or the 0.1 seconds later, no, it's the same exact time. That's why it often involves collisions. If a huge truck and a small little butterfly collide at the same time, even though it might be hard to understand, they are applying the same amount of force. Okay, so they're applying the same amount of force on each other. For every action force, there is a reaction force equal in strength or magnitude and opposite in direction. So the force when something collides is the same. Whether the impact, like the butterfly, will obviously be hurt more, but the force exerted on each other is the same. So two objects, one force on each. The force AB means the force on A by B. These forces cannot cancel each other out. So they're not canceling each other out. Yeah, that's right. Got two objects. So two objects. A, comma B means force on A by B. And these forces cannot cancel each other out. If object A applies a force to B, then B applies an equal and opposite force on to A at the exact same time. Two objects, force A on B. Okay, let's now let's talk about tension and friction, and then that'll be it. Oh, there is that force. So even though it's the same amount of force being applied at the same exact moment, there's still that force. Because it's not the same object. Right, so there's a difference between, say, someone is punching another person, that is Newton's third law. But if it's just an object resting on the table, it's at rest, so the forces cancel each other out. So then it's not Newton's third law, because the net force is zero, and that's because it's on one object. When Newton's third law is saying two objects. So in the punching example, the two objects would be the hand and the face it's punching, for example. While that object, it's just one object. Okay. Friction, or let's talk tension very quickly. Tension is just force of the rope or whatever that's pulling back. So if there are two people, so now we're talking about tension. If there are two people pulling a rope, the middle is that. So if it's like 50 here and 50 here, the tension is 50. The tension not 50 plus 50. The tension is just 50. Do not add them up. Okay, and then friction, and then we'll be all set. So third line. Oh, another thing I want to quickly add about Newton's third law is just this formula, not really formula, but vector force A on B equals opposite force B on A. Okay. Now let's talk about friction. Okay. Friction depends on mainly two things: what the two surfaces are made of and how tightly the surfaces are preserved together. Normal force. So, right, if the material that's so for example, ice, that has pretty much no friction, but maybe like sandpaper that has a ton of friction. The friction depends on what the two surfaces are made of. Friction depends on what the two objects are made of. And number two, how tightly the surfaces are pressed together. So normal force. So this is a little confusing. You might think mass might be one of them, but it's not. It's normal force. So let me just add here, rough or smooth. Okay. Static friction, two surfaces are at rest with respect to each other. Kinetic friction, two forces are moving with respect to each other. So the difference between static and kinetic friction. Static friction is what keeps the box from moving without being pushed. Right, so remember, so if you you know how when you're moving a very heavy object such as a cabinet, the beginning push is static friction. It's hard, but then later it gets a little easier, and that's kinetic friction. So static is like the beginning. So you need to get past the initial static friction before pushing gets easier, and you get to kinetic friction. And yeah, that is it on the video. Thank you for watching.